to answer. First of all, how to recognize where you are. Feel yourself a Columbus, traveling from Europe to he didn't know where, searching West India or whatever, and how did he manage to know where he was on the deck of his ship? The question is complicated, however, mariners from the ancient times were interested in this question and they knew how to do that approximately. First of all, we have a map. Actually, our globe has a system allowing us to know where we are, to know where we are on the coordinate map of this globe. We have parallels and meridians, and these parallels and meridians on the northern or southern hemisphere, on the eastern or western part of the globe, tell us where we are. So, to know where we are, we just need to know our geographical coordinates in grades and minutes and so on. One of the fathers of cartography is Mercator. Mercator was an advanced scientist of the 16th century. His name was Kramer, Gerhard Kramer, and as it was accepted at the time, he just translated his name to Latin and obtained that Mercator. Maybe in Spanish his family name was Mercador. The main result of Mercator, at the moment it looks some doubtful, however his name is already in our history. He offered what we call cylindrical projection map. So he created a map which represented globe in paper. The question is how we can project spherical surface to the plain paper. Cylindrical system, Mercator system, means that we preserve angles. So in his map, all the meridians were parallel. This type of map is more or less accurate on the equator, and you cannot see the both poles in this map, and northern countries would be magnified. So, for example, Russia looks at his map much more great than it is in reality. However, Mercator is in our memory, and due to him we have marine maps, aero navigation maps, and so on. Travelers, mariners or pilots, they definitely need to know how to get from one point to another point. And there are two ways of doing things: loxodrome and orthodrome. Loxodrome is a beautiful way of doing things at Mercator map, because in his map all loxodromes are just direct lines. So you can just take a ruler, connect 2 points by a line, and that is your road. Then a pilot, a navigator, has just to keep the angle between the meridian, between the direction to the north and his course due to this line, and at some time his ship or airplane will arrive to the point where he wants to go to get. Taking in mind that our world is spherical, not that as it's shown on Mercator map, we can see that orthodrome is preferable, and orthodrome is the shortest way between 2 points on the globe. You can see here how many kilometers we can save choosing our travel using orthodrome. For a long time, orthodrome was quite complicated, but now, of course, it is a reasonable way of navigation, especially for aircraft. So, how to know where we are? The first idea is to find out what parallel is here. You can see here so-called Jacob stuff. It's just a way of measuring the height of a star over the horizon. In fact, our latitude is just a height angle between polar star and horizon. So it is enough to measure this angle and you know your latitude. So if you know some trigonometry, you can calculate this angle using these sections OC, OA, and just do it. Of course, staying on the deck of your ship with the roll and in maybe some fog, the process doesn't look that easy. But it was used for ages. Then next generation astrolabe. There were several types of astrolabes, and astronomical astrolabe is a complicated device. However, mariners used the astrolabe just as I told you about Jacob stuff. The same idea of the measurement is just measuring this angle over the horizon. Sextant is a modern way of doing things, so it is a complicated optical tool, you can see it, and sextant is, I would say, state-of-art way of navigation, of doing navigation. So mariners know pretty well how to do it. You can see here this girl, definitely a navigator, is measuring the height of the sun. It is not necessary to measure exactly polar star. If you know your date and time, you definitely can use the height of the sun. So you can see that a sextant allows us to do your measurements quite accurately with the accuracy of minutes and seconds. However, still not enough accurately. What about longitude? Measuring longitude means measuring time. And the idea is just using clocks and timepieces. So our prime meridian or Greenwich meridian is just a line on the globe where the longitude is equal to 0. So if you know time difference between prime meridian, Greenwich meridian, and your local meridian, you know your longitude. So the idea is just to have a precise watch, actually timepiece or chronometer, showing Greenwich time, and determine a local time using, for example, a sun watch. And the difference will be your longitude. The idea, more or less precise idea, or I would say technology of doing this was developed by Gemma Frisius in 16th century. And you can see him, his representation, and his paper, according to which he proposed us his method. The first task is to know Greenwich time at the arbitrary point on the globe. Today it looks easy. You just need to have a watch. But in medieval ages and in 18th century it was a problem. Good chronometers were invented where actually implemented only in 18th century. You can see here chronometer H1, first more or less workable chronometer by Mr. Harrison, and you can read that British Parliament introduced so-called Longitude Act, actually offered some money, a reasonable amount of money, for a person who can create a reliable chronometer which could be used for marine navigation. The story, the history, I would say, about these chronometers and this Longitude Act race is very challenging, very interesting. And you can see that in 18th century some models of chronometers were more or less ready for using in marine navigation. Next point is how to know your local time. If you have a smartwatch, you can definitely measure the midday, for example, and this midday depends on your longitude, definitely. However, you can see these graphs, and you can see that true time needed for longitude determination depends on several effects. So we have elliptical orbit, we have orbital tilt, we have to say other problems, and only 4 times a year your local solar time is equal to the true time needed for navigation. And the deviation could be reasonable, 15 minutes, 10 minutes, so your measurements depend on time. This is more or less modern chronometer. You can see the certificate, chronomètre de marine, of course Swiss, and this tool is more or less suitable for our longitude determination in 20th century. Next task is to know where to go. Knowledge about your position is pretty, but not enough. You want to know where you are and where to go. So the most, to say, ancient tool is compass. You can see Chinese compass on the right. Looks very doubtful how precise, how accurate it was, but it was a compass. And at the left you can see more or less modern compass used in the ships, and the idea of the compass, you definitely know it pretty well, is just an idea of using magnetic field of the Earth. We assume that magnetic pole, north magnetic pole, is somewhere close to the North Pole, and this compass shows us where this North Pole is. Of course, if you are on the deck of the ship containing a lot of steel and a lot of devices using electromagnetic fields, you can have some errors due to this fact. And what is more important, magnetic pole and North Pole are not the same. So you can see here that magnetic North Pole is drifting quite quickly, and now it is maybe more close to the North Pole than 40 years ago, and after some dozens of years perhaps this magnetic pole would be somewhere on the Russian territory. And this deviation of magnetic pole from the North Pole is very important, especially if you are a pilot or maybe navigator somewhere in northern country. If you are going to the pole, this magnetic North Pole is interesting. Next, to say thing necessary for navigation is lighthouse. Lighthouse is very ancient. Some of the lighthouses have a very ample history, and for example, lighthouse of Alexandria was miracle. He was in the list of the miracles, and these lighthouses are just towers with some light showing mariner how to bypass maybe islands or banks and how to get to the port safely. All the navigation methods described before are not really accurate to allow this navigation near the heaven. And you see that what we just need a powerful light source and a high tower. Why the tower should be high? Because the higher the tower, the farther we can see our lighthouse. You can see here the formula. The L is a distance in nautical miles and H is height of the tower in meters. So the limit of the visibility of these optical lighthouses is maybe a couple of dozens kilometers. That's all, but it is enough for to get to the port. If you came, for example, to your haven approximately plus minus 10-15 kilometers, it is enough to have a lighthouse to get exactly into your port. How to do the things better? Light is maybe not to say the most reliable way, however it is visible. If you use radio waves, you maybe is able to increase the visibility of your lighthouse, and using some tricks you even can convert this lighthouse idea to positioning. Not only where to go, but where we are. So here you can see one of the most popular radio navigation systems. It is hyperbolic navigation system. It consists of 3 stations, actually transmitters, master transmitters, and 2 slave A and slave B transmitter. They should emit radio waves synchronously. If they emit radio waves synchronously, and if you have a receiver on board of your ship, you can measure the phase difference between the radio waves of these master and slave B and slave A. These hyperboles, they are the lines where this difference would be permanent. So, for example, at this point, or at this point, or at this point, you will have the same phase difference using master and slave B. The same idea could be used for master and slave A, and the cross of these hyperbolas would be your position. This is a very, to say, fruitful idea, and it was implemented in Deca system. Deca system was used in the 20th century in Northern Sea, Baltic Sea. To say these seas are not safe to navigate. The conditions are quite complicated, a lot of fogs, a lot of banks, a lot of shallow places, a lot of islands, and so on. So mariners definitely used this system with great pleasure. Actually, the idea is hyperbolic. You have these stations shown on the slide. You can look at this map and estimate how it was. The Deca was used, by the way, at the D-Day, so this in 1944, to bypass minefields and to know where to how to get to your point on the coast of Normandy, and it was workable. It was used till perhaps the end of the century. I'm not sure, but I think the last stations were disabled maybe already in the 21st century. You can see here that we have a lot of systems of radio navigation, and Omega and LoRaN and others, and for example VOR DME, which is used for aviation. So our pilots bring you to the airport using this radio navigation VOR DME, and it is workable now. It is state-of-art system. In 1957, first satellite of the Earth was launched, and this event was definitely the beginning of a new cosmic epoch, and as well it was a new epoch for navigation, because the satellite moving along the orbit, parameters of which we can calculate, is a beautiful lighthouse. You can see it from great territories on the surface of the Earth. And actually, during the first flight of the first satellite, several experiments were carried out. Because Doppler navigation, using that changing of the frequency of the onboard transmitter, is also a way of navigation. So we have some purely Doppler navigation systems. They are a bit out of the topic. However, you can say that from that time, space navigation started. What is the idea? If I have several satellites somewhere above our head, and if I somehow know how long these satellites at the moment are from the receiver, I can draw these spheres, and the cross point of the spheres would be exactly the position of my receiver. You can say that from geometrical point of view, there could be 2 points, 2 cross points, but the second cross point would be far from the surface of the Earth, and we can easily exclude it. So to have our satellite positioning reliable, we just need to have a lot of satellites flying around the Earth. At the moment we have 4 global navigation satellite systems. I would underline the word global. These navigation satellite systems are close to provide more or less accurate positioning through all the surface of our Earth, of the Earth. GPS and GLONASS are maybe the oldest systems. Galileo is now evolving system, European system, and Beidou became global only a couple of years ago. At the moment, the number of Beidou satellites is the biggest. So, for example, at my city, I can see maybe from 6 to 10 GPS or GLONASS satellites and about 2 dozens of BeiDou satellites. The number of satellites is maybe not a guarantee, but the key for precise positioning. If we are looking at the GPS, it contains 3 segments. Space segments, that's satellites, user segment, receivers, and control segment, used by the authorities to provide accuracy of the system to perform operations like maybe time corrections, diagnostics of the satellites, and so on. It is necessary to understand that user segment is just the number of receivers. All global positioning requires only reception, no transmitters are used. What concerning GPS, the central control point is the military air base in the United States and Colorado Springs, and several control stations located at Hawaii, Ascension Island, Diego Garcia, and Kwajalein. These stations are more or less close to equator, and satellites moving around the Earth get the information and transmit the information to these control stations. In Russia, GLONASS stations are located within the territory of the Russia, and you can see that again we have some control stations, monitor stations used by GLONASS. What concerns receivers, receivers of our GNSS positioning systems are more or less the same. I mean, the structure of the receivers for all systems are similar. It is just a radio receiver with radio frequency front end, low noise amplifier. Then the signal is digitized by the ADC, analog to digital converter, and then we have 2 stages like acquisition. Acquisition is the first order measurement of the distance to the satellite. Actually, the distance to the satellite is measured using time interval. If we know the time delay between the moment when the signal was emitted and received, we know the distance. After this first order approximation, we use receiver channels. I mean that all these yellow blocks are just blocks tracking their satellites and correcting the distance, getting information, getting correct position of a certain satellite for all visible satellites, and this information is used for position calculation further. As for GPS, we have a specific way of doing things. I mean that every satellite transmits its own unique code called CA, course acquisition code, and this code, along with the data, navigation data, is transmitted using binary phase shift keying. I mean that the signal is a harmonic signal, sine, the phase of the sine is changing at the moments of all the edges of these pulses. This is a generator used for that, and this generator produces gold code, and the gold code is unique for every satellite. Using different points S1 and S2 for the feedback of these linear shift registers, we obtain unique CA code using for positioning. How it is used? These gold codes have very interesting characteristics. These characteristics are characteristics of autocorrelation and cross-correlation. I mean that if I had two signals, shifted one relatively another for some time, I can calculate their autocorrelation function. If these signals are properly aligned, we have a peak, very narrow peak of this correlation. Various gold codes, different gold codes, have no peaks. The level of their cross correlation is low. So the idea of measuring the distance to the satellite, actually measuring time delay, is just comparing the received signal with known code and your local copy of this gold code. And here you can see more complicated, more detailed representation of a GNSS receiver. Few words: antenna, front end, down conversion, and this picture above, this one, is just a picture showing us how we can perform acquisition. In fact, acquisition is an operation needed to find out whether a certain satellite is visible, and if it is visible, what is the approximate delay of this signal and what is the Doppler shift of this signal. I'm not sure that all of you know what is Fourier transform, but Fourier transform is the main method of this acquisition. In fact, we have our local copy of the code, gold code. We modulate it by a specific Doppler frequency and compare with the received signal in the frequency domain. After this operation, we obtain the graph of our autocorrelation function shown before, and we can find the peak, and if we have a peak, it means that we have the signal and the position of the peak is just a delay. The picture below represents tracking. Actually, we generate our gold code, local copy of gold code, of early, prompt, and late type. I mean shifted one from another for a short period. And then we calculate the correlation of the signal in this correlation module. The satellite is moving, the distance is changing, and the receiver itself also can move, so this position is drifting. Tracking module tracks the distance between the satellite and our receiver. This information is then transmitted to the navigation processing unit, where our position is calculated. Actually, at the output of our tracking modules, we obtain pseudo-ranges. Pseudo-ranges are just time intervals. Being multiplied by the velocity of light, we can obtain the distance. Why they are pseudo-ranges, not real ranges? For several reasons. First of all, our gold code has a limited length. So our correlation can provide you a time delay within an interval, maybe for several milliseconds. And this time shift is a key information. However, the satellite is far from the Earth. actually about 20,000 kilometers or more, and several distances can give us the same time shift. And we do not know exactly what time is now at the receiver. All the satellites typically emit their signal synchronously. They have atomic watch on board, but we cannot afford atomic watch at all our GPS receivers. However, we have all this information. You can see these equations. Actually, our pseudo range can be calculated like this. If we know satellite position, and we know it, we have a technology, and this technology allows us to calculate the position of the satellite at every moment. And we introduce this delta t. It's just an unknown time shift between the real time atomic clock of the satellite and the time of our receiver. Having 4 equations with 4 variables, we can resolve it. You can see that the system is not that simple, at least it doesn't look simple, and we resolve it by some mathematical tricks like numerical methods, for example, and after resolution we obtain our position. We have several things interfering the process. For example, we have ionosphere. In the ionosphere we have some physical effects, and these effects create additional delay, and additional delay means errors of our distances, and then these errors will result in our erroneous position. We have the troposphere, and the satellites somewhere near horizon definitely undergo refraction. I mean, signals emitting by them undergo refraction, and this refraction again introduces additional error. Then in what we call urban canyons we have reflected signals reflected from the walls, from different obstacles, and these trajectories, you can see they are not correct distances to the satellite. And these arrows with different polarization again affect our accuracy. Typically, navigation signal have what we call right-hand circular polarization. After one reflection, this will be left-handed circular polarization, and after 2 reflections, again right-hand circular polarizations. And this is like to say in the mirror room, and all these trajectories can add our ambiguity, add our errors of the reception. To overcome the problems, we use augmentation systems. Augmentation systems contains what we call reference stations. One of them is master station, and these stations have well-known, precisely measured positions, and measuring the pseudo ranges between these stations and positioning satellites, we can estimate these ionosphere and troposphere delays. Then we can transmit this information to the receiver, and the receiver, for example, pilot, can use this information to correct the errors I have mentioned just a couple of minutes ago. So these augmentation systems are present in the United States, in Europe. So this is again a part of what we call positioning. Then a couple of words at the end of my lecture about educational programs in GNSS technologies supported by Samara National Research University. What do we want? Actually, our goals you can see here. We want to provide a world-class level of education in the area of GNSS, and not only. Our education is arranged to provide you a wide range of skills, not only GNSS, but also electronics, FPGA skills, and SDI, and so on. And of course, for you, I mean for our future foreign students, we are trying to support comfortable conditions and international curriculum and so on. The main program we propose is about GNSS receivers, hardware and software, and this program is to say arranged in the framework of radio engineering. It is the master's program, so the students with bachelor diploma are welcome for it. You can see here main courses within these programs. I'm not inclined to discuss all the courses in details. You can see them here, and of course the program could be slightly different depending on the situation, and some signals could be chosen or not chosen, and depending on the situation we can try to provide flexible educational trajectory for you. You can see here that the set of the courses is to say focused on positioning technologies, I mean algorithms of position calculations, and also we use courses about radio receivers, about digital devices, about algorithms, and so on. So after the graduation from this program, you will be, to say, comprehensive specialist in radio engineering, but with the focus on GNSS. Our main focus in GNSS technologies is about SDA approach. So we show you how to use software-defined radio for GNSS, how to use software and hardware in combination or maybe solely, how to use DSPs, FPGAs, and so on. So we are trying to support state-of-art level of our GNSS technologies and the knowledge we are giving to you. Of course, we are trying to support you in this learning process. So, for example, we offer academic English course. It is useful for your master thesis, how to create readable and to say reasonable documents, how to use terminology, how to use real English in professional environment. And our attitude, I think, is student-centered. You can see here the group. At the moment, it is a group graduated in 2018, and you can see some people from Latin America here. Of course, we have some conditions for get modern, I would say, highly professional education. Our program has been recognized internationally, so it is recognized by European agency, and this is again a word for us. If you want to apply for the program, I recommend you to look at the page here. You can always call us, write us, and our officers responsible for the recruiting of foreign students are always ready to help you. You are welcome to Samara University. All I wanted to say. Hope that my lecture was more or less interesting for you. Hasta pronto.
Muy bien, entonces, estimada audiencia, era la ponencia del doctor Iliá Kudriátsev, investigador principal de una de las cátedras de la Universidad Aeroespacial de Samara. Quisiera precisar que la maestría que él lidera en esta universidad se dicta tanto en idioma inglés como en idioma ruso, y justamente hasta mediados de este mes se encuentra abierto el registro para aplicar a una beca académica que les permita a aquellos que deseen participar estudiar de manera gratuita en idioma inglés o en idioma ruso. Y para ello estamos dispuestos a ayudarles, a orientarles, como siempre, a hablar México, a hablar Colombia, a hablar Perú, a hablar Bolivia, a hablar Ecuador. De manera que les invito a que se interesen por esta maestría, aquellos que están dentro de su rama, y participen. Como les comenté al inicio, el doctor Iliá Kudriátsev tuvo un imprevisto, un viaje de último momento a la ciudad de Moscú, pero se preocupó en pregrabar la presentación. Por eso es de que esta ponencia no cuenta con el espacio de preguntas y respuestas. Les agradezco bastante su atención, y por hoy día, en ponencias relacionadas a ingenierías, hemos llegado a su fin. Les invito a unirse mañana. Mañana partimos, sí, ya mañana partimos a las 7:30 hora Ciudad de México con el quinto día y el tema Periplos gastronómicos por Rusia, un curso muy interesante para aquellos que están estudiando idioma ruso, pues complementa la inmersión cultural que ustedes deben de tener antes de viajar a Rusia. Seguidamente, una conferencia relacionada a la gestión de operacionalización del modelo de aprendizaje automático con Streamlit, a cargo de un magíster en ciencias de la Universidad Federal de los Urales, quien se encuentra actualmente culminando sus estudios de doctorado. Y luego la ponencia en vivo del doctor en ciencias Uglanov Dmitry de la Universidad Politécnica de San Petersburgo, referida a la energética clásica y alternativa. Entonces, les agradezco de momento por su presencia hoy día y me despido hasta mañana. Muy buenas tardes.